these notes. Basically, we're just going to draw one really nice FBD on this sheet of paper. Make it big, take up the whole side of a page. Okay. All right. So far, everything we've talked about with friction and tension and all that has been mostly flat surfaces. Okay? But today, we're going to go into situations where we are on an incline. All right? Ski season is starting. Okay? We have a ski club here. So, you guys want to get involved with that? All right? Yeah. Okay, our first trip is to Telluride, December 6th, by the way. Okay? Alright, we'll talk about that later. Alright, now, on an incline, some of our forces that we know about start to act a little bit weird. Okay? So we could have a ski hill, a road, a ramp, okay? Any kind of incline this will work for. Alright, a hiking trail. Alright, so usually, don't we draw our axes like that? Y is vertical, X is horizontal. Okay, now here's where it gets weird. With ramps, what we do is we tilt the axes like so. Okay, so on your pages, just draw the slope. In other words, draw the snow. The ramp, the incline. And then, with dotted lines or a different color, draw the x-axis as the ski slope, and the y-axis is drawn perpendicular to the slope now. And that helps us out with a few things when we start drawing the forces on here. We need to be good at drawing this FBD. We'll have to do it a bunch of times. Okay, now we're not going to actually draw the skier. We're just going to draw the skier as a dot. So even though on the PowerPoint the skier's center of mass is really right here, on your drawing, to simplify, draw a big dot right at the crosshairs. And that's going to represent the center of mass of the skier. Okay, so let's diagram the forces. How am I going to draw mg this time?
Still straight down?
Still straight down. Okay? The center of the earth is where? Is it over here or is it right here?
Right there.
Right there, the second one. Okay? That is mg. Okay, so maybe you want to switch colors. Something like this for your force vectors. And we'll label it mg. Okay, that's the force of gravity acting on the skier. Alright, what other forces are acting on him?
Normal.
We got normal, what else?
Friction.
Friction, we're going to assume there's friction in this situation. Okay, anything else?
Maybe apply
Wind resistance is kind of friction, yeah.
Is there like momentum?
Well, on an FBD we only do forces though, so we won't include momentum on there. Okay, so let's draw normal. Now, what does the word normal mean? Not in like a, not like normal person. In physics, normal, what's that word mean?
Support.
Okay, it is a support force, but the word actually means something. Perpendicular. Okay, normal means perpendicular. So here is the surface. So far in this class we've only done flat surfaces. Normal is acting perpendicular or straight out of the slope. Okay, at a 90 degree, right here, there's a fly in here and it's attacking me. Okay, right here to the ski slope. Alright, now friction is going to be like that. Okay, is friction always uphill?
No.
Doesn't have to be. If the thing is sliding uphill, friction would be downhill. Alright? But this situation, it's uphill. Okay. That is your FBD. If this is a test question, and it says draw all the forces on the sled or the skier or whatever, you stop right here. Okay? Now off to the side, we'll need another diagram with the components. Okay, so down here we got theta. That's the angle of the slope. Alright, so we put that down there. It could be a road. In this case, the angle of the ski hill. This is a super steep mountain right here. Alright, now, can you guys see this big triangle right here? Okay, and we got theta down there. If I do this, can you see that this triangle is, in math terms, similar to this triangle? Okay, you guys know that? The similar triangle theorem, postulate theory or something? Okay, I'm not going to teach you the math part of it, alright? But because of similar triangles, this angle is always the same as that angle. Now I'm going to take these away for a second. Okay? We just kind of have to memorize that. Between MG and the negative y-axis, you will have a theta equal to the incline's theta. Okay? This is always where we will put it. Alright, now, I'm going to use that theta to break mg into its components. Okay? So here is the y component of mg. Alright, now, this gets weird too. Which side is this with respect to theta?
Adjacent.
It is the adjacent side. For adjacent side, we use cosine, correct? Okay, so we're going to say this is mg cos theta. Now, it's weird because we're using cosine along the y-axis. Usually we're using sine along the y-axis. Okay? Alright, this down here is mg sine theta. It is the opposite side of the mg triangle. Okay, now this down here sometimes is called FP, or force parallel. But I don't ever write that because then students are like, oh, there's this magical new force. There's not. It's just the opposite side of mg. Okay, but it's called force parallel sometimes because it's parallel to the slope. So what does this thing actually do to the skier?
Accelerate.
Okay, that's the drive. Yes, that's the force that is going to drive them down the hill. All right. Well, it's the component of mg that is going to drive them downhill. All right. Okay. Now mg cosine theta. What does that force or component of force do?
Keeps them on.
It keeps them on the hill. Okay. So if I just had normal force and mg cos wasn't there, wouldn't the skier fly off the hill according to my diagram? According to my diagram, not in real life, obviously. Okay, but what this does is balances out normal. Okay, and the forces in this direction are 0. Okay. All right. What else? We might put F net off to the side. If mg sine theta is bigger than the force of friction, then the skier will accelerate. If mg sine theta is the same as the force of friction, if it's kinetic friction, the skier will be going constant velocity. If it's static friction, the skier will be standing on the hill, going nowhere. Okay? All right, Zach?
What if you have the skiers doing an applied force with this pole?
Okay, yeah. Now we could have all kinds of other forces. The skier applying the force with their poles. We could have a cable pulling the skier in some direction and involve tension, which we will. Okay, probably not with skiers, but yeah, we will involve some other forces later. Okay? All right, any other questions about this? Okay, yeah.
If it was like that, would you have to add FA to like MG sign, or I guess we'll come.
Depending on which direction the force applied was in, yes. Okay, now dig through your notes. There's an example we have not done that says example 17. And it should be on the... Let's see. It looks like this. Alright, Ben, is that camera focused on the screen there? You think they'll be able to see that alright?
Yeah.
Okay, cool. Alright, so this one involves a skier as well. Okay, so we've got a 30-degree slope here. We're going to assume the coefficient of kinetic friction is 0.1. Draw an FBD. Okay, they already did that for us. So there's the FBD. And it's the same one we just drew. Let's go and add the components of gravity on here. Okay, so this is mg cos theta. And this is mg sine theta. And we got some values. We would like to calculate her acceleration down the mountain. Alright, so we do an FBD. What do we usually do next? N2L. Alright, Newton's second law. So let's say right here, F net is equal to what? Okay, what's the force? Well, first let's start with y direction. What are the y forces doing? They cancel out, okay, and then there's going to be some x forces that are unbalanced. So the driving force is this one right here, mg sine theta. So we're going to say mg sine theta minus our force of friction. We'll just call it force of friction for now. And we're going to break this down a little bit at a time. Okay, now what can I always replace F net with? MA. So we'll say MA equals mg sine theta. And instead of writing that, let's put the fun equation. So minus mu times the normal force. Okay. We'll leave that as MA. We'll leave that as mg sine theta. And we're breaking this apart one step at a time here. We'll leave this as mu. Alright, but normal force. Okay, what can I say instead of big N there?
mg cos theta.
Okay, so here's normal. We know it's balanced by that component. So we say mg times the cosine theta. Alright. We want to solve for acceleration.
That's why m.
Okay, we like canceling stuff here. Okay, not you, Celia. Sorry. Okay. Alright, now do you guys see that I've got an m in every term? Okay. We're not given the mass of the skier. So all I have to do is cancel all of the m's. Now remember, it's not because I have one m on either side, or it's not because I have an m on either side. It's because I have an m in every term that I can do that. Okay? If I didn't have an m in this term, or I didn't have one in this term, I couldn't cancel them. Okay, you've got to have an m in everything. Alright, so we're left over with this simplified expression. Acceleration is g sine theta minus mu g cos theta. Alright, and at this point, there's no other ways to simplify it, so we'll go ahead and plug in numbers. Alright, so do that and get the acceleration. Alright, and rounding to 2 sig figs, we'll get 4.1 meters per second squared. Okay? Yep.
How important is sig figs for this?
Well, you know, sig figs or sig figs. Sometimes we're loose with the sig figs. Okay? Since the mu has 0.10, I rounded it to 2. Okay, alright, other questions? It's pretty good acceleration. If you're on skis, you're going to feel that. Alright? So, let's calculate the speed she will reach after 4 seconds. This is a kinematics review. So, what do we know? We know time equals 4. We know acceleration equals 4.1. And what's kind of implied, but maybe should be given to us?
Vi equals 0.
Okay, starting from rest maybe, right? Okay, so VI is 0. Alright, so we've got a handy equation that says the V final is the V initial plus AT. Alright, VI goes to 0, so we get V final equal to 4.1 times the time of 4. Okay, we get 16.4. Alright? Yeah.
If we could, no, yeah, never mind.
Alright. Okay, how many of you have been skiing in the spring when the snow is very, very slushy? Okay, is slushy snow fast snow or slow snow? Slow snow, okay? If you get into slush, that's what happened at Russia, right? Last Olympics.
Oh yeah.
Didn't they have problems with slow snow? Okay, the problem was mu. The mu at the Olympics was too high. Alright? So, right here, suppose the snow is slushy and the skier moves down at constant speed. They're not going to accelerate. Okay? What is the coefficient of friction? Alright, we will start out with this statement. Constant speed, anytime you see those words, you should just write down F net equals 0 somewhere. You'll probably get a point for it if it's a test. Just write F net equals 0 if you see that. Okay? Alright, so instead of putting MA for my N2L expression, I'm going to put 0 is equal to, and then I'm going to use the same thing I used right here. But instead of setting it equal to MA, I'm just setting it equal to 0. So I'm saying 0 is mg sine theta, being canceled out completely by mu mg cos theta. Okay. Now what I want you to do is take this term, this big ugly thing, and move it to the other side. Okay? So we get that. Those two forces are equal. The downward force is equal to friction. Okay, now this time we get to cancel even more than last time. The m goes away, but what else goes away?
So does the G.
Okay, this whole thing goes away. So if I solve that for mu, which is what we want to find, mu is equal to sine theta over cosine.
Yay, which one's mine?
Okay, now maybe somewhere in math your teacher taught you trigonomic identities. Alright, and you were taught to notice that sine over cosine is simply what? Tangent. Okay, good. Oh, you guys know that. Okay, so mu is equal to tangent theta. Not always. Only in this situation where we've got an f net of 0. Up here, not the case. Alright, so let's plug in tangent theta and get an answer. Okay, if I rounded correctly, I got 0.58. You guys agree?
Yeah.
Okay, that's a much higher mu value than 0.1. Is that realistic? I'm not sure. Okay, snow and skis, that looks a little bit high. Okay, but that would be the mu required to keep the skier from accelerating on that type of a slope. Okay. All right, what's the unit that I put here? Trick question, no units, right? Okay, mu is a unitless quantity. All right, okay, Nick?
Do we need to simplify the last step? Are we going to miss a point?
No, you're not going to miss a point for not knowing your trig identities. But we try and connect math in here as much as possible so you guys can see where some of these things can be used. Okay, what else?
Well, I was going to say, like, instead of using your VF is equal to VI plus AT, you could, like, look at the acceleration and know the velocity graph of that is actually 4.1x, but again, that's just connecting math, so I was just thinking that you shouldn't connect math all the way.
Okay. Alright, Jamesy.
So would that be like for any instance where it's not accelerating
Yeah,
down slope?
It
we just
sure
use
would
that?
be. Now, we can also use it for this. We can use it for mu static if the ramp is angled to the point where we are going to get maximum static friction. Okay, that would be like if you took a block, put it on a ramp, and increase the angle. That angle at which the block just budges is going to give you mu static if you plug that angle in here. Okay? Alright, cool. Okay, that's good. Alright guys, on